So last line there, printf, is actually using this size of operator. So that operator was something we had introduced a little while ago. And its job, right, is to go to a particular data type. And we've used on things like ints, for example. But to go to that data type and tell us how many bytes that data type takes up. So in this case, it's trying to figure out what is the size or what is the number of bytes required by this struct course. Right there, you can see it says size of SER334. Well, what happens is on the inside, right, in the compiler, it's going to look at that and find out what is the type of SER334 and return the size of that type. If I wanted to, I could have written that line a little bit differently. I could have done something like size of, open parenthesis, struct course, close parenthesis. And that would be equivalent to what I have here. Point is, again, we're getting the size of something. So maybe take 1 second to ask yourself, how many bytes does this take up? So maybe you think to yourself, okay, I can kind of look at this, and I need space to store each of these 4 things. So what I need to do is basically figure out how big each of them is, and then add them up. 4 bytes for my integer. 4 bytes. Maybe I'll just draw bigger here. Actually, I'm going to clear that real quick. SLN this is going to be our 4 bytes here, because that's the size of an integer. Title 256. Well, each byte is a char, or each char is a byte, so that's going to be 256 over here. Let's see, instructor 250. Again, 1 char per byte. An int over here. Well, that's going to be 4 bytes. So let's see, let's add that up. So go 4 plus 256 plus 250 plus 4. So 514 is what we would hope to get from that. Unfortunately, if we run this program, we're not actually going to get 514. We'll actually get 516. And let's actually take a look at why. So this is C, right? This is low-level stuff. We have to worry about some things we don't normally worry about. One of them is what is called structure padding. So I have that my declaration of my struct up top. I have the 4 parts of it. Let's see how it could be laid out in memory. So you can imagine, right, is that you have this basic thing here in the middle, somewhere in memory, right? So this is, basically, at position 0, and this over here is going to go to position, it's actually be 516. We'll explain why in a second. Instead of 514, right? If I just add up the sizes of everything in the struct, then it ends up being, I wrote the number wrong as I was speaking to that. It should be 516. There you go. All right. So it's basically starting at 0 over here, right, going to 516. That's the size of our struct. So if we look at how this is going to be laid out in memory, well, it's going to be laid out basically in the order that the struct is defined. So the first thing in the struct is the SLN number. So basically the first part here is going to be 4 bytes for the integer. Okay, fine. Then I have my char, which is basically going to be a string for the title of the class. That's 256 bytes. That's fine. It'll go in there next. And then here, next thing is I'm requesting 250 bytes for a string for the instructor name. So I do 250 bytes. Okay, that's fine. But then the issue here is that 250 isn't a multiple of 4. What does that matter? Well, what it matters is this. So let's say you're on a 32-bit architecture, and your CPU needs to make a request for a piece of data. It's going to request a piece of data which is an entire word, right? So you manipulate basically 32 bytes, right? That's how much you can read at a time. Technically you can kind of read 1 byte at a time, but generally, right, the idea is you're reading this chunk of data, right? What is the basic word length of your system, right? That's going to be the basic amount of data you either read or you write when the CPU is manipulating stuff. Well, if I have this set up where I have 250 bytes for instructor followed directly by time, well, then I'm going to have at time it's basically going to be a piece of data that's not aligned with a word. So basically 2 bytes are going to be in one word, and then 2 bytes are going to be in another word. That means I need to do 2 loads in order to access the value stored inside a time, because it's not aligned, right? It's not aligned to a multiple of 4, and I can only load those multiples of 4. If I have a piece of data that's only 4 bytes, but it's basically making use of the last part of one word and first part of another word, well, then I'm going to need to load both words, right? Load 8 bytes in order to actually manipulate that thing. Even though it's only 4 bytes itself, because it's not aligned, I have to access both parts. So this is an issue. It's going to slow us down. The way to address that is to add some bytes for padding, and this is what will happen automatically on most compilers. So what will happen is the compiler will look at that instructor variable and see that it's 250 bytes, realize it's not a multiple of 4, and so add a number of bytes after it in order to bring it up to be the proper length of the word. So in this case, it's doing a padding by 2 bytes to make sure that that next variable time will be word aligned, right? So it'll be located at a multiple of 4 from the beginning of the memory for this particular structure. Now, if I had things set up a little bit differently, maybe I wouldn't need padding. Sometimes what happens is that, we could have in here your char instructor 250, and then maybe I have, char A, char B. So maybe I had a couple of other variables in there. Well, they would maybe form that padding. Sometimes what happens is people even shuffle things around, right? They'll change the ordering of the pieces of data inside their struct in order to make sure that there isn't any gaps, right? That everything is aligned with a multiple of 4. So you can do it manually. The main motivations for this, right? The first one, right, is speed, right? Again, we don't want to trigger, 2 basic reads or 2 writes instead of 1, right? When 1 is all we really need. And also, right, to minimize how much space we're using, right? So if we're on something that's maybe a mobile device or something that has very little hardware available or very weak hardware available, well, then we really don't want to have all these pads and maybe we'll waste our precious storage memory. So if we can implement our system so that there's no padding, then that's going to be beneficial, right? There's going to be more memory for us to use on stuff overall. So here's just a final example. I said it earlier, right, that the dot operator was the main way to change things to have a struct. There's also another operator we can use as well, and that's what's shown here. So some boilerplate stuff again, right, our include files, definition of a struct, talked about that earlier. Here we're creating 2 struct variables. You notice these 2 are slightly different. So the first one is me creating a struct variable called SER334. 222. Second one is me carrying a struct pointer. So that second variable there, SER360, that is a variable that contains the address that points at a struct. So it's indirect access, right, instead of direct access. Instead of having a variable that directly stores that thing inside there, instead of that, we just have a pointer. So it's a little bit different. The first example, we'll use this, right? We use this kind of direct method to create a variable. That's actually going to be a stack allocation. Or here it'll be a static allocation because it's a global variable, but it's kind of a static thing. It can happen ahead of time. So looking at the code here, this is what we did before we did the dot access, right? So we had our SER222, we're using our dot, and that's fine because that variable SER222 is containing the struct itself directly. It's not containing the address of a struct, it's containing the struct itself. So we can directly go to it and access stuff on it. Now in case the other variable, we'll have to treat it a little bit differently. So you'll notice here, the first thing we do is this dynamic memory allocation. So what we have to do is say, okay, I'm going to go to malloc and ask for enough bytes to store this particular struct. So I'm doing my malloc command there. You can see I'm sending it size of struct course so I can get the number of bytes that are required, requesting them from the compiler, and then requesting them from the runtime environment, and I'll get back a pointer that gives me that much memory. And then that pointer, right, that address will be stored into CSE360. So now my variable is set up and I have memory allocated for that second course, but it's allocated in terms of an address, right? I have a pointer to it. I don't have a variable that contains it directly. Now in this case, I have to use slightly different syntax. So because that's a pointer, I'll have to use something like that star operator basically to dereference it. So I can go my star CSE360 that turns my actual address of a struct into an actual struct, and once I have that actual struct, right, once I have that direct access, I can do .sln in order to access the number of that course. And then I can do that assignment, same as I did in the previous example, the code above. So that's one way to do it, but it's a little bit annoying because you constantly have to have that star there, you have to put the parentheses around there, and then you can do your dot. So it's some overhead that's kind of just annoying. Well, the other way to do this is to use the arrow operator. So the arrow operator, we're using the final 2 lines here, and what the arrow operator is doing is it's combining the star and the dot. So the arrow operator is the equivalent of saying star and dot, right? So those 2 things are going to be equivalent there. That first line there, the star CSE360.sln, and then the next line is CSE360 arrow title. Those are basically doing the same thing. That arrow, again, is just replacing that dereference followed by a dot. So the arrow, you'll see a lot in code because it's just showing that somebody has a pointer to a struct, and then they want to basically go and look up the actual data that's stored there, and then do the dot on it to change with something that's part of it, change one of the member variables. So you can combine both those things into using the arrow operator.